If you are building a career in academia, then you know that PhD is a huge milestone. But what comes next? How does one really make a mark and navigate the global research landscape? What is the best time to start writing research proposals? If you are wondering about these questions, then today's podcast is for you. Stay tuned. Welcome. This is Ananda Biswas, and you are listening to the Decoding Phase Transitions, the DPT podcast, where we decode the fascinating career phases of brilliant minds. If you tuned into part 1, you already heard Professor Andreas Kreisel, who is also a physicist, share his fascinating journey through early academic life up to and including his PhD work. We explored the initial challenges in higher education and how research is truly conducted. You might also have noticed that he has this amazing power and ability to make complex concepts comprehensible and clear in a manner that anybody can follow. You can check the link of part 1 here or in the description box below. Now in part 2 of our conversation, we are moving beyond his PhD and into this next exciting phase of his academic career. We'll delve into what motivated Professor Kreisel to move into the US for postdoctoral study and his experience of moving across continents. We'll also get his unique perspective on differences between the US and European research environments and discuss the ideal time for young researchers to start writing grant proposals. Beyond the career path, we'll dive deep into the heart of his scientific work, exploring the state of the art in superconductivity research and explaining what it means to have conventional versus unconventional superconductors. Plus, we'll touch on the teaching process in higher educations and rewards and challenges that comes along with it. So get ready for another insightful discussions with Professor Andreas Kreisel. Welcome back, Andreas. Thank you for being here. And today is the part 2 of our conversation. In part 1, we had discussed your early life, early interests, up to your PhD days. What was your question? How did you solve it? What are the learnings you got out of it? And today we'll focus your journey from there. You went after your PhD to the US, to a new culture from Germany. Before that, you had some exposure to other cultures. As an exchange student, you said during PhD to Brazil. Today, you tell us about your postdoctoral experience and why did you want to stay in academia and why did you choose University of Florida and Peter Hirschfeld as a PI?
As you said, the point after my graduation was this question of whether or not to continue in academia. And I mean, my decision was, in a sense, governed by sparked interest in first learning more about the topics I was exposed to, and then second, also the joy of doing research, having contact with people from other countries, from other cultures, and then also the whole community of researchers that, meet in conferences and have nice discussions, both on scientific points, but also on a little bit more the personal development since the last meeting or the last time one had some contact with. And for the decision to go to US, it was kind of at that point one of the best places to actually do research, because there are so many institutions, there's so big research community, and there is also this freedom of research and the possibility to explore many things. And that led me made some search to find postdoc positions, which was a little bit hard by that time because I didn't know so much about other topics. I applied to quite a number of positions, an order of 10.
But everybody does that, right?
Everybody does that. And I was also, in many cases, not so successful between the message thank you for your application, but we have found somebody else. To no reaction at all to my application. So therefore, I was quite happy that actually for a post on doing research on unconventional superconductivity, I was quickly contacted by Dieter Hirschfeld that he actually wanted to make an interview and talk to me to kind of figure out whether there might be a match. Let me explain a small anecdote on that, because that actually happened during one of my trips to Brazil. So actually the interview with Peter Hirschfeld was set up while I was actually not in Germany, but on my trip to Brazil.
But was it the Brazil trip was the end of your PhD when you were also searching for your postdoc?
Yes. So that was actually a trip that was done after I had actually finished my PhD and was staying for half a year in Frankfurt. And I actually had signed an interim contract for a postdoc at another university, by that time at the University of Kaiserslautern already, to go there for some months to bridge the time for until I find a position. So the situation was I had that interview, kind of after a very short time I got offered the position, but then I had to cancel the other position.
Yeah.
Remotely, actually. So this was quite some organization helpful, but I was very happy. And then, I mean, the whole process of moving to another country.
Can I interrupt you here? You said the anecdote was that your interview was from Brazil. And did you want to say something more there?
Well, I mean, okay, by that time, this was also a little bit unusual in the sense that could not get any feedback from my supervisor or whatever how to do this interview. But in the end, it worked very well. And I mean, I have been now a long time collaborator with Peter Hirschfeld, and I could understand now much more how he did that interview and the reasons why
he chose you.
Even though I did not have a lot of preparation or build out a research proposal or whatever.
So what do you think in hindsight, people who are preparing for this kind of postdoctoral interviews, what they should have in mind and what they should prepare for beforehand?
Let me say, I didn't have too many.
But now you know, because you said I
know a little bit, and my proposal would be try to be neutral and try to kind of be open to any of the discussion. That is the most important thing, and not prepare for questions or prepare your ideas or whatever. Often that's not the important thing. The important thing is that there is also a match on the personal side, that your coming a supervisor actually kind of likes your personality, likes your approach, and bringing this through an interview, whether it's in person or whether it is in Zoom, or by that time it was actually Skype.
Would you say that some of the personality traits as a researcher that are helpful for educational or research environment are perhaps open-mindedness, ready to collaborate, a team spirit? Do you think these are the qualities that a prospective employer or the postdocs are looking for, even for doctoral candidates, I would say, right?
Yes, I would think that's very important. Let me say it's very important to the research groups I was exposed to at the moment. So it might deviate a little bit if the community is a little bit different or different research groups. And maybe it's also the reason why I entered this particular research group, because there was a match. So I'm not saying that a person that has not these qualities cannot be a researcher.
Sure.
It might be that there is another match of another supervisor who wants a slightly different approach, has maybe also some different research agenda, which is less towards collaborative or common problem solving, but is more about directed problem solving and then afterwards discussion. So, I mean, I wouldn't say
Sure.
inclusive.
Yeah, there is opportunity for everybody.
Yes.
Yeah, perfect.
Yes.
And so then you were selected as a candidate, and then you went to this whole new country with a different cultural setting.
Yes, I mean, let me say one thing that, I mean, my supervisor and also some other professors in Frankfurt, they had also been exposed to the US research culture because also during their time of PhD and postdoc, they were in US. So there was already quite some spirit of collegiality and how you interact with people in Frankfurt present. But of course, many of them administrative tasks and the way how the university is organized and the way how teaching is organized is quite different in US that I was then exposed to. It's also a completely different type of life that you start with all the struggles as moving to another country, getting the bureaucratic things, the visa application, which probably nowadays, unfortunately, is even a little bit more complicated because of the political situation in US. But by that time, it was also for me quite a bit of a difference in that respect. And then the final move there, traveling and starting a new household there and organizing all these things is quite stressful and give quite some uncertainty. But I'm very happy having done this step, and I'm very happy for the time I spent there, and I made a lot of friends.
In your opinion, what is the major difference in the US and in Germany or in Europe as a whole in research environment?
At least for the PhD time in US, it's much longer. So it might be that you enter as a PhD student the corresponding topic much more deeper than you could do in the 3 or 3.5 years that is common in many European countries. So that is one difference. And the second difference, I think, in US, the kind of flexibility of the topics that a PhD student is pursuing is a little bit bigger. So in Germany or also in Denmark, there is this strict time constraint. The PhD program runs 3 years, maybe can be prolonged by a 4th year, but then it has to finish. Then, I mean, the supervisor has to have a quite concrete plan in which direction the research project should go. And there is also quite some pressure to propose a project that is prosperous and that is working out. In US, I'm not saying that projects are just proposed out of the blue, but I'm just saying that there is a little bit of flexibility. If after 1 year or so, some project turned out to be not the most successful one, there is still some flexibility and time to move to a slightly different question and still have a major contribution. Let me point out one thing which we also talked before, the differences between theory and experiment. There, from the research infrastructure, it's quite some difference because theoretical groups, at least in the US, they can also keep working if there is no funding or not much funding, because usually PhD students are paid for teaching at the university, and then in their remaining time, they can work on their projects, which can work easily for theory projects, even if the PI currently doesn't have funding. For experiments, it's much more strict because if there is no funding, then often the lab cannot be run, which is sometimes happening such that some research branches drain out, despite the fact that there is in principle lab equipment, but which just cannot be run because of missing funds. And that is in Germany normally not happening because there is a long-term coverage for running of the experimental setup. So that's some difference, but okay, of course, this is not something a student or a postdoc should be worried about when applying or moving to other countries.
Sure.
The eye has to make sure that there is a possibility to make research.
But sooner or later, they will be introduced to the concept of funding. And it's good to keep in mind that it's also dependent on the continents, perhaps, and in the countries, particularly how the research is run and how much aid you can have from the institution also, and how much aid you have to gather from funding. This is, I guess, the early introduction to funding concept.
Let me say at this point also that for the application for funding, as a young researcher, one should not wait too long. So this can already start before actually finishing the PhD, that one might apply to funding and agencies to get funding for a postdoctoral appointment or some exchange program. So it really starts in earlier career, and then it has the advantage that even if it doesn't work out, often there is a second opportunity to get a position or continue in research. But then one still has gotten some insights and went through the process of submitting a proposal and knows from the feedback what one did wrong or what one could do better in the future time. And let me also mention that many of them research grants are really targeting young researchers. And often there is also a constraint on how long you're allowed to be after your PhD defense to submit some of the grants. And that one should try to not miss these deadlines and try to submit some of the proposals. And there are many opportunities, both national ones, I mean, either from Germany or from US or from the European Union, where one should really try to get into and try to apply. Of course, the current supervisor is always a good point of information, and one should talk to the people in the department. They know what is possible to apply and what is prosperous.
Yeah, I think that's a very good suggestions and very important information also. What I understand now, that if you are serious about staying in academia, then you should try to write a proposal for a scholarship, for a funding when you are going abroad, or even in your own country, what is available. Because as you mentioned, Andreas, that even if you fail, you go through the process and you learn how the system works of writing funding. And writing funding is a good skill to have in your later life if you stay in academia, because you will perhaps do it more often in your later life. Even I had heard stories from people that even if you fail, mentioning the failure is a plus point than having no experience in applying. So it's a kind of that. So have some experience in writing funding, or some proposals to get some kind of scholarship or some kind of postdoctoral scholarship.
Let me mention one other topic here, which is in the preparation of making such a project proposal, you always have to go a little bit out of your comfort zone of the research topics And in most of the cases, at least in my case, it turned out that I learned something on a slightly different topic, which in many cases I could then use later on also for additional insights in ongoing research projects. So therefore,
Always, it's a positive, yeah.
Broaden your knowledge, and if the funding is approved, you gain something out of it. If it isn't approved, you also gain something out of it because either you know a little bit more about this other topic, or you even might know why your proposal was not considered to be as good because there are some concerns about the research methods or the prospects of positive outcomes which other researchers might have in the reviewing process. So,
or it broadens your perspective of problem solving and gives you idea, as you said in your personal experience, that you could use some ideas and tools your current problem. So that's always, again, thank you for pointing this out. So you had told us about your research interest getting diverse at this moment when you went for your postdoctoral studies and you studied unconventional superconductors. You had experience with quantum magnets before, and then you switched to unconventional superconductor. Tell us about your research and what are the questions, and in a broad sense, what do you mean by unconventional there?
Yes. So the big difference between the research methods, let me say, in this case, is that during my PhD time, I was mostly looking at articles called bosons, which follow the so-called Bose statistics and exchanging them. And then moving forward, I was not looking at bosons so much anymore, but at fermions, so the electrons in metallic systems, and then asking the question of what interactions for electrons can do. And one phenomena which is seen in many metals at low temperatures is this phenomena of superconductivity, which, broadly speaking, is well known because of the possibility of having currents in metals without losses. And that has quite some application, and that's always the nail that one puts into forward when, as we have just discussed, putting forward some research proposals. Now, the interesting part from the perspective of superconductivity is that it's, again, a collective phenomena. So it is a phenomena which is qualitatively different from a single electron properties. So it's driven by quantum mechanics. So it's, again, governed by something like a Schrödinger equation, which for a single electron, one knows the properties of the electron in the atom. One can have properties of multiple electrons around an atom, but that is qualitatively different from the properties of a superconductor, where, again, the quantum states are is a collective coherent state between many interacting electrons, and this gives rise to this so-called Cooper pairing, where kind of electrons form bound states of Cooper pairs and can then form a microscopic quantum wave function, which has this intriguing properties of superconductivity.
Can you talk about coherence? How can one simply understand coherence?
Yeah, so I mean, one hallmark of superconductivity can already be understood if you think about the properties of wave functions on an atom. So when one goes back to the Bohr model of the hydrogen atom, then one knows that there is only allowed quantum states when the quantum wave function around the atom matches to kind of the boundary conditions such that it's continuous around the atom. But that's now on a scale of the size of an atom, where this quantum mechanics plays a big role. Now, for a superconductor, exactly this property of that the wave function is continuous holds for the total wave function of many electrons, and that can now also give rise to macroscopic centimeter size properties. Now, you can take a ring of a superconductor, that's the metal ring that is connected, and then in the superconducting state, the electron wave function or the Cooper pair wave function has also to fulfill this continuous condition, but now not on a scale of atomic size, but on a scale of macroscopic size. And this condition then gives rise to properties that one can actually measure, for example, as tiny magnetic fields that go through such a ring, where one actually uses so-called quantum interference to see small magnetic fields from measuring the properties of the superconductor. So this is an intriguing and quite difficult to understand quantum phenomena. It's not for a reason that the understanding of superconductivity in history took already 40, 50 years between the original discovery of superconductivity at low temperatures and the theoretical understanding, which was in the 1950s of the last century. But still now there is a lot of material science going on to discover new superconducting materials. And part of my research back then, when I started my postdoc and still now, is to understand the superconducting properties of materials and use a macroscopic quantum wave function to learn about how the electrons interact in condensed matter systems.
Thanks for this nice explanation, very vivid. And then the question is that there is a TC involved for the superconductor called the critical temperature. And this TC is for all existing superconductors is very low. And the idea of the research is to advance that temperature higher towards perhaps room temperature.
To go back 50s, 60s years in history, there was kind of some materials known that have this property of superconductivity, but only at very low temperatures, 10 Kelvin, 20 Kelvin. So really cold temperatures where you needed liquid helium to actually cool the system. And for using this thing in order to make for example, a coil that can sustain magnetic fields without losses, one really has to cool down a lot. And therefore, much of the research was and is still driven to find superconducting materials that have this property at higher temperatures, and probably the dream is to have it actually at room temperatures. This was partially fulfilled 30, 40 years ago, when there was the discovery of so-called high-temperature superconductors, which were some not simple metals, but which were some compounds made by copper and oxygen, the so-called cuprates, where it was found that the phenomena of superconductivity was present at 100 Kelvin or even higher, so you only need liquid nitrogen to cool it. However, after this discovery, the rise in critical temperatures kind of flattened out, that not so many new compounds with even higher temperatures were discovered, with maybe a small exception of some materials which show hallmarks of superconductivity at very high pressures, which for the application is, however, not so prosperous as well, because these high pressures where you need to put the material actually between two diamonds and press on it to get actually the conditions to make it superconducting. So therefore, one direction.
And the pressure itself changes the phase of a material. So therefore, there are a lot of complications that come in.
I mean, for application perspective, I think at the moment there is no way to get this material system in a phase where you can actually make a wire and use the wire to transport electricity or to use it for other purposes. However, what has been driving recently is that the superconducting state itself has a plethora of different phases, which we call different superconducting phases or different superconducting order parameters. And there is quite some research because it's not so much the prospect of using it as wires, but the prospect of using a superconducting wave function, this large-scale wave function with these interesting properties to learn about how quantum mechanics works and to use this superconducting wave function actually for something that is related to actually using the quantum states as computing bits, so to build a so-called quantum computer, which in principle can solve mathematical problems much better than the nowadays available computing units, which are based on circuits that just use the electronic transport as kind of to store the information.
You talked about the superconductors having application in quantum computing, and the research is going on towards pushing the critical temperature up higher and higher for the high ETC superconductors. A dream is to have the room temperature superconductor. What are the applications of those room temperature superconductors? This can conduct current and without losses. So what would be the applications then for these kind of superconductors?
Our daily life is very much governed by using of electricity. So it's a big problem of transporting electricity over some short distances, long distances. You have all these conductive losses. So that would be one possibility of reducing our energy consumption or reducing the energy consumption from the transport. But it's also the possibility of having, for example, engines with coils and superconducting magnets that actually do not have the losses from running the current. So it could be that, the other one talks about electrical cars or about other electromotives or whatever. That could reduce the power consumption significantly. Same is for power generation. So if you have windmills, a part of the force is actually lost, or part of the wind energy is lost in making heat in the power generator. On the other hand, there is also the possibility of making all types of circuits, whether it is in your mobile phone or whether it is in all types of devices, where 90% of the energy is just lost by the
Conducting the current.
Conducting the current. And if it was possible to partially or fully substitute this with materials that are superconducting, this would be a great step forward. But I think at the moment we are not yet there. It's mostly a dream, but one should not give up this dream and
Sure. And I'd actually also go a little bit far and say it will revolutionize the way we perceive everyday life. It will totally change the way devices work and devices look. So it can affect our everyday life hugely.
And let me mention some motivation to go into the research of solid state physics or condensed matter physics with the knowledge that in the recent centuries, or I mean the recent 50, 100 years, the revolution of daily life was always connected to scientific progress in material science and solid state physics. Just to let me to talk about two examples. One is finding of semiconductor physics in the 1940s, 1950s, which led to the discovery or the fabrication of a transistor, which changed our daily life enormously by all the devices of electronics which we have nowadays. Another revolution came probably some years later when the properties of magnetism were discovered and investigated from a research perspective, which led to the possibility to store actually information on magnetic systems. So in the early days, it were just kind of the tapes where you could record music or information. Later on, this was revolutionary the data storage for computers because all the hard disks were based on and are still based on magnetic materials. And there is also a lot of research going on to miniaturize the magnetic moments where you store the information and to optimize readout and storage in various ways. And all these things are directly connected to research efforts in the years before. So that's a great motivation to enter actually this field of solid state physics.
Perfect.
I apologize for this advertisement of our.
You have to do it because now
I think it's really important.
People should know and people should get aware of the fact that research, even in their small steps ahead, they are contributing to their everyday life of people. So it's also a great motivation so for the researchers that even if it doesn't feel like you are doing a lot, but collectively as a community, going forward one step at a time also leads up to great discoveries at a later stage. So this is what we had learned earlier from all these great discoveries. So it matters. Yeah, you said this is a big dream of superconductor having the high TC, and we had also worked on one of our project together with our collaborators, where we also talked about this unconventional nature of the superconductivity. So you had long experience with this. Tell us a little bit about what is unconventional. I think we didn't touch it before.
Yes. So, I mean, to go a little bit into the detail of this research question, one has to touch upon some concept, which is the concept of some order parameter. And to give just an example, for such an order parameter, this is, for example, given by the order parameter of a magnet. So if you look, for example, at a piece of iron, we all know this is
magnetization.
Has this magnetic properties, and then at high temperatures, the iron does not have any magnetization, and once you cool it down to some low temperature, it actually acquires the finite magnetization, which is the property of the ordered state. Now, for a superconductor, the corresponding order parameter is somehow related to the Cooper pair wave function. And here the order parameter is actually related to something which is called a non-Hermitian expectation value in quantum mechanics. So to give a little bit the background, in quantum mechanics, one talks about so-called operators, which have some mathematical property, which is hermeticity. And it turns out that all operators which are Hermitian can be related to a quantity which actually can be measured in experiment. So an example of a Hermitian operator is, for example, the energy operator. So you can measure then from a theoretical point of view, you can calculate the energy of a quantum state, which is then directly measurable. Now, Hermitian operators have the property that the expectation value or the measurable is just a real valued quantity. However, if you have such an operator which is not Hermitian, then this quantity can be a complex number. And a complex number is directly not measurable in experiment. Now, for a superconductor, as I said, this property of the order parameter, which tells you whether or whether not you're in the superconducting state, is related to a non-Hermitian operator. So it's directly related to a quantity which is a complex number. Now, for conventional superconductors, this complex number is usually considered to be a constant. And by some mathematical tricks, which are by choosing the so-called correct basis of where you describe your Cooper pair wave function, you can actually make this expectation value or this order parameter a real positive number. And that is one hallmark of a conventional superconductor. Now, for unconventional superconductors, this possibility is actually not there anymore. And this order parameter is not a constant number for the so-called quantum numbers of the Cooper pair wave function. And in the simplest case, it's just a function that is positive somewhere and negative for some other choice of quantum numbers. In a more complex setting, it's actually, it can even be inherent a complex number such that you cannot remove complex nature by a choice of the basis function. And then what these are then Cooper pair wave functions which break additional symmetries, for example, the time reversal symmetry. And then we are talking about more exotic superconductors, so-called chiral superconductors, which have the property that it's related to that the symmetry between the left hand and the right hand is broken, and that brings in new properties when you actually try to observe interference of these Cooper pair wave functions from right-handed states with left-handed states. And that has interesting properties to see the quantum nature of such a superconductor. And that is some types of questions which we are actually currently investigating, with looking at possible materials where certain types of superconducting states are realized and figuring out what are the consequences of such exotic unconventional pairing states.
Thank you for describing it in a understandable way for aspiring researchers and for the community. Let's move from here to a little bit lighter topic. You take teaching very seriously, and you are a very good teacher, what I had gathered information, and I have seen it firsthand because when we were collaborating, you taught me a lot of concepts. You also later took the decision to do a habilitation, which is also habilitation particularly is a highest academic degree one can have in a university. Especially this is important in Germany and other European countries. And people generally are encouraged to pursue independent teaching and independent research. So you have a lot of teaching experience in University of Leipzig and otherwise. What are your favorite courses to teach? And what do you think that you will be excited to teach in the next 5 years if you were to conduct a new course in physics?
So, I mean, let me just go back a little bit. So, of course, when I was appointed at my position in Leipzig, this came together with teaching duties where I had the opportunity to actually teach in one of the undergraduate courses, because Leipzig University is one of the few German universities which actually has English taught physics bachelor program. And there, I worked quite a bit, quite some years with undergraduate teaching, so first year and second year students, to introduce concepts of theoretical physics to the students, which gave me also the challenge to bridge between different background knowledge of that students, because the international program in Leipzig was and is used by students from different backgrounds. Some of them are from Germany, some of them are from European countries, and some of them even outside Europe, from Asia and US and Africa and so on, giving the problem that a lot of students have quite some different background. Some of them are proficient in mathematical concepts. Some of them might be lacking some of the background information. And there, I tried to pursue the idea to teach the basics to all students, such that it's understandable, and then the more challenging and more specialized topics then left to exercise classes and left to the very good students. But I wanted to make sure that all students understand the basics and understand the general concepts, rather than putting out all the details and putting out all the specialized topics for the whole class.
How did you separate out these specialized topics to target the good student only later?
Well, it was mostly done with the exercises. So, I had the lecture part where most of the base was discussed, and I also tried to put on in some simple examples and lay out all the concepts. And then in the exercise classes, which in principle everybody had to look at, but which were not required to hand in terms of that they were counting towards the final grade. It was only that you had to work on each of the problem, and if the student has trouble with it, then it's also fine, as long as everybody at least tried to understand the problem or try to work on it. And then the discussion was then done in the exercise classes.
I see. So there was no grading based on the assignments or the Hausaufgabe, as they say in Germany.
We had hand-ins to give feedback to the students, but let me say the requirement was that you were actively participating, whether it was in hand, or whether it was in the class by not solving the problem, but asking questions on the problem to actually demonstrate that you were working on it, and demonstrate that you had some trouble understanding it, then it's also completely fine.
Mm-hmm. What courses did you teach?
Well, this was, as I said, first and second year courses. So this was Mechanics 1, classical mechanics, Newton mechanics, and then it was the 2 electrodynamics classes. So it was electromagnetism, and then electromagnetism 2 with advanced mechanics, where there was also relativistic mechanics and Lagrange and Hamilton mechanics. So it was quite a challenging classes, but I think the majority of the students actually made a very good job. One has to again say, and we were talking about this earlier, that indeed in the first 2 years, quite a number of students dropped out. But that was is the usual thing that is happening in science education, especially for study programs where everybody can sign in. But it's then good to have a clear cut for students that realize that physics and with the requirement of the background knowledge of math might be not matching the personal.
Yeah, and what would you teach in next 5 years if you were free to choose any subject?
So, I mean, for the teaching purposes, there is, I would think, two parts of the story. The first part is, of course, the duty and thing of educating a new generation of physicists or engineers or whatever. But then on the other hand, it is also possibility to attract people to research directions and potentially also to theoretical physics or theoretical condensed matter physics. And the second is then a little bit towards designing lectures or teaching opportunities that are a little bit higher level, that are for master courses, that are give some emphasis on some research directions and potentially make people interested. And then the other part, the duty is, spark the interest and, make the new generation of students be prepared to learn more extended topics. However, unfortunately, when you work in a big department, there is also some boundary condition, namely availability of courses for me or for anybody else. So one has to adapt a little bit.
It's a hypothetical situation. Let's say you are free to choose subjects to teach. What would you teach?
If I was selfish, it would be some advanced course on, for example, magnetism, or advanced course on unconventional superconductivity, to really combine my research interests with also talking about these topics to students. Let me also say here that even though you might be an experienced researcher and might know a lot about your research topics, you always learn something new while preparing the topics for a non-expert, and that also brings forward quite a little bit on the research forefront. So therefore, that's what is probably the direction I would like to go. But however, introductory topics are also very interesting. The students are so curious about everything and they question everything. So I always have a lot of fun when also talking.
So what is the most rewarding aspect of teaching for you?
The most rewarding effect is actually to see the result of the teaching, in the sense that you follow the career of the students that you have taught maybe in the first semester, second semester, and see that they master their curriculum, and that they go either in the direction of your own research or go to other groups and benefit from what they have learned in your own lecture.
You have a very long teaching career, in the sense you started as a PhD student, you went to tutor and had some experience teaching there, and then also until now you are continuing it. So do you find any challenging aspect of teaching, and according to you, what's the most challenging aspect for teaching the university students?
I would think one challenge that you need to be flexible, and flexible in the sense to change your way of teaching or your way of presenting things according to the needs of students. And that sometimes comes a little bit short, because you have taught the course before, you might be stuck a little bit in the daily teaching that you had your topics and the way you presented it, and it becomes a little bit laziness in not altering the topics too much. But that's what you always have to do, and that is always what at some point lacks a little bit in the style. But yeah,
the fact that you think about this, that from the student's point of view it might be difficult, your current style or current way, it already proves that you are a good teacher. You had just said that even if you are a seasoned researcher, you still have to learn a lot on a regular basis, because field is moving on and your research interest is also evolving. What is your method to learn deeply and quickly anything?
I mean, what we do very often is something like journal clubs. So in our group, we have a weekly meeting where we read one or two papers and then really discuss about it, and also really go into the basic questions of this research topic, and then also let the students ask basic questions, and then often struggle a little bit around in answering the questions, because also the experienced researchers don't know it. But then as a result, you always gain out something of it. And even if it is just the finding that we are not sufficient knowledgeable to understand this research direction, which is a little bit outside the comfort zone. So that's important, and that's how we approach it here in this case.
And how do you choose the papers for the journal club? Is it like the presenter is free to choose, or as a group it's decided that these are the papers which are coming out in recent days and seems interesting, let's put it as a journal club and discuss it?
I would say it's twofold. First, I mean, of course, everybody can propose something, but sometimes for the students, it's a little bit difficult to find the most interesting or the matching recent papers on archive or recently published ones. So that's a little bit a disadvantage. But sometimes the papers are also chosen according to the projects of the students. So we have some topics, whether it's superconductivity or magnetism, or some certain topics that students are working on their master thesis, and then once in a while there is a paper chosen for each of the students in the group, and then it's also a little bit the discussion between the students that then everybody knows a little bit about the details that the other people in the group are discussing.
You were saying that you have a lot of experimental collaboration. You also have other theorists whom you collaborate with. So when you approach a problem, there is a lot of discussion, and there is a part also you work alone, right? What is your mental model to proceed to a problem? How do you formulate a problem in a way when you are working alone? And is there a favorite thought experiment that you go back to check your ideas?
The types of problems we are trying to solve theoretically, they are sparked by experimental findings. So new materials, new measurements, some open question on this part. And then the second part in solving, or I mean, not solving, but designing the research problem is to figure out what ingredients are needed to formulate the theoretical problem and potentially solving it. And if the ingredients we need can be all done within our group, we might just start the project within the group, and then I mean, together with the student or the postdoc or whoever is involved, to get this question done. But if it turns out that some of the ingredients or methods we are not proficient with, then we might reach out to other groups. To just give an example, if it is a material-specific question, we might reach out to a group doing ab initio calculations, like we also did in our common project, where some part of the project we are not the truly expert, and then this part is a little bit split up, and then of course sometimes it does not work to ask one or the other group because we cannot influence the research directions of other groups. But very often it is a common interest, and then a new project is born, and then it gets formulated.
Do you have a method when you are stuck in a problem? What do you do? How do you go ahead? Is there a systematic approach to it?
That's a very difficult question. I mean, let me say I was once in a while was stuck in problems, and very often we just put it aside and then did something else, and then eventually came back to on a similar point, but with some additional knowledge of the side project, or some additional knowledge from the experiment. So, for example, if it's about materials, then there might be some property of the material that is experimentally not known, and that is inherently difficult to calculate, but which is needed to complete a project. And then sometimes, for example, the electronic structure is actually measured in an ARPAS experiment, or is deduced from other properties like specific heat or so on. And then one can adjust the input needed for our theoretical calculations, and then go back to the project and have a good starting point, or a good starting Hamiltonian, how we usually say, and then go back to the project and potentially finish it. But there is no guarantee, and sometimes also the experimental efforts are very difficult and might not lead to the desired output from our point of view.
Yeah. That happens often, that on both sides, when we get stuck, you approach each other and then to figure it out again from experimental point of view, what extra they do know and what can they perhaps include in the next experimental setup. So I would say it's both ways, right? Experimental and theoretical collaboration goes both ways. It's not that experiments are leading and then we are just following. Sometimes theory can lead and then see the outcome and perhaps inform the experimental collaborators. See, this is what we are seeing. Maybe you can design something to check it. So it goes hand in hand that way.
And let me also say that, and that's just from my experience of difficult problems, that usually the difficult problems lead actually to the most prosperous research outputs once we have managed to actually solve the problem. And sometimes this comes back after quite a couple of years, where we then go back to the topic and actually make a contribution. So,
do you have a favorite story here, like that you got stuck and came back to it with more knowledge, and it was at the end came out to be very important piece of work in the field?
There is one example, which is a material I have been working on quite a bit, which is this iron selenium superconductor, which has some interesting properties in terms of the present phases, and has this property that it's a non-magnetic material but shows symmetry breaking from so-called tetragonal system to orthorhombic system. And the question of the influence.
You're talking about the nematicity.
Yes, I'm talking about the nematicity. And an early question was the question of the role of the nematicity in terms of designing or defining the critical temperature. And we wanted to understand actually from a theoretical point of view, what is the evolution of the critical temperature as a function of pressure. So there had been experiments and experimental attempts to investigate that probably more than 10 years ago right now. And we were trying to attack this problem from a perspective of material-specific calculations with help of actually the group in Frankfurt to make the material-specific prediction from the lattice structure to the electronic structure to the superconducting structure.
Mm-hmm.
But that project actually got stuck, and we could not find any mechanism that could explain the experimental data. And then later on, we found out that this material has this very strong effect on the electronic structure from the nematicity. So despite the fact that the lattice structure is only changed by less than 1%, so the atoms in one direction come only closer to each other by 1% and go away in the other direction. But there is an order of one effect on the electronic structure. And once we understood that this is an important ingredient and how to model this ingredient, we could make some steps ahead to understanding the superconducting structure. And still now we are working on some aspects of this material to understand tunneling on the surface of this material and trying to understand superconducting order parameter from various perspectives.
It's funny that you mentioned this because in the group in Frankfurt, I was also involved and I did also some ab initio calculations on this material. It is fascinating, and maybe now we can discuss about your next move. You are moving to further north, as you had mentioned to me earlier, that you were moving to Uppsala University, Sweden, as an independent researcher, as a associate professor. Is that correct?
Yes. So, I mean, that's at least what I'm at about to prepare here. So, yeah, so my time here in Copenhagen will soon be come to an end. And I mean, I'm very happy to go one step further in my career, and actually I'm preparing to move research direction, and also it's some interesting time, despite the fact that location wise it's a neighbor country, but then one has always the joy in entering a new administrative system and entering a new system of how things are organized and overcoming all the trouble, which you probably also know from your own experience by moving from any country.
Yeah, it takes a while to settle down, but many congratulations for your new position, and you are going to build your own research group. Could you tell us a little bit about what research direction you are aiming to build there? And if you want to share once you go there, if somebody is wanting to join your group, how they can reach you. There will be proper application, I guess, from the university side. There will be an advertisement, and perhaps one can keep looking at the university side during that time. Can you give us a timeline?
So, I mean, of course, not everything is decided yet. So, but I will certainly stay in the research direction of unconventional magnetism and superconductivity, and actually bring in a little bit of a bridge of this topic, because in Uppsala there is a very big group doing ab initio investigations for magnets. And there is already a group doing model-based calculations and calculations for topological superconductors and semi-metals and all of this direction. So I see myself just in between these two research groups. Regarding details on opportunities to collaborate with me, I unfortunately don't know exactly the time scale, and I'm a little bit unaware about the processes because, as I said, to the Swedish system. But as you said, I mean, there will always be some timeline of advertising positions. That probably the best place to look at would be somehow my webpage or posts that I will put forward once I actually know about these details as well. Let me mention here that in general there should also be some possibilities to apply for external funding from Swedish agencies. So if somebody is interested, of course, it might be a possibility to contact me directly, and once I'm settled down, I will certainly consider applications or grant applications from possible.
So then, if you are listening to the listeners, I would say that keep looking at Andreas' webpage, most probably from next year onwards, and then also keep looking at the funding possibilities and approach Andreas. He is willing to take your interest and applications and guide you through it. So we are at the end of our conversation. Only a couple of fun things that maybe we'll do it quickly. That might be interesting. So what are your hobbies?
Well, I spend a lot of time out in the nature. So whether it's hiking or going with a bike, that's where I spend my weekends, and that's also why I'm very happy to go to mid-Sweden. There should be a lot of opportunities to see the great nature and spend some time there.
Great. How many languages do you speak?
That's a difficult question. Of course, I mean, my mother tongue is German. Then I speak English as it is needed to communicate on a scientific level and also here. And then recently here in Denmark, I also learned Danish. And then I have some small knowledge of some Romanian languages. So I know a little bit French from school time, and I also learned a little bit of Portuguese, actually Brazilian Portuguese, because I was in this exchange program.
Yeah, perfect. And then one is going to add to this list in the next 2 years. I see it. Swedish will be added to the list. Knowing
Yes.
you, I'm pretty sure you are going to be an expert in that language too. So, do you want to mention any role models that influenced in your career, your life in a big way?
During my study time, quite influenced by my peers. So the group of study colleagues where we spend quite some time doing some joyous things, but also spending some time to understand physics and solve the very difficult the tasks we had to do in a couple of semesters. But then, I mean, in terms of mentors, I'm very grateful for my postdoc mentors. I mean, this is the group in Florida by Peter Hirschfeld. I mean, he's a great collaborator. He's a great mentor in many respects. And I'm also very grateful for the mentoring that Brian Anderson did here in Copenhagen. So we are longtime collaborators, and I mean, it's always the first point of open questions regarding all sorts of trouble that could arise.
Yeah, we had in our podcast Shinibali Bhattacharya, who has also Peter Hirschfeld as her PhD guide. And she also shared the same experience that he's a great mentor. I am hoping to have him also one day in my podcast. Thank you for sharing it. Last question. A lot of people today are questioning whether they should do PhD or not, whether it is important or not. If they want to stay in academia, this is an essential a step. One has to go through this. But otherwise, people are already thinking whether it's necessary. It takes a lot of time. It's nothing they had experienced before, because until then the academic career looks in certain way. They can know how to gauge their progress. Each day is something else, and each journey is unique. So looking back at your own journey, do you think that it taught you something in life other than the degree, especially to give some idea to these people who are wondering about this question?
Let me say, doing a PhD has some additional degree of learning compared to your studies or the master degree, because first you gain quite a bit of independence. And second, and that was true for me and is also true for many students here in Denmark, that it's the first opportunity to actually move to another country, get exposed to the research direction in another country, and also have the opportunity to experience the daily life in another country. In my case, it was South America. In many cases here from the PhD students here in Copenhagen, it's travel US and see there how the university works and how a research group works there. And that not only gives some insights in academia and opens some possibilities to move on there as a postdoc or so on, but also gives a lot of insights from a personal point of view. Even though some people might just after their PhD say, okay, it's not for me, but I think everybody has gotten out a lot of experiences that you cannot and will not do in your life afterwards.
Yeah, I cannot agree more. I really think that PhD has shaped my life in a way that I had become another person, and I'm happy about the person I have become. It's subtle and it's a long journey. In some countries, some countries it's not so long, but it definitely teaches you more than only just the academic degree. And thank you for sharing all your experience, Andreas. Where can people find you? Are you in LinkedIn? Is your webpage enough if people want to contact you?
Yeah, probably just search my name on the internet and you will find the contact information. And
okay. Yeah, I will also put the link of all these things below in the description box, or wherever you are listening your podcast. You will see all these things in the podcast notes. Thank you, Andres, once again. Thank you for your time. We were delighted to have you here. And thanks for sharing your invaluable experience with us.
Then thank you. And thank you also to you, Sananda. It was fun to talk to you and all the listeners.
Thank you. Bye-bye. And that brings us to the end of our conversation with Professor Andreas Kreisel. From understanding his drive behind the postdoc in the US and navigating different research environments, to gaining insights into the critical timing for grant proposal, we have covered a lot. We also had a fantastic discussion on the physics front. We explored the cutting-edge superconductivity research and the challenges and reward of teaching in academia. Professor Kreisel have shared his invaluable perspective on this episode. We hope that it will inspire and inform many of you. It's been a true pleasure of having Professor Andreas Kreisel, across these 2 episodes. And thank you, my listeners, for tuning into the Decoding Phys Translations podcast. If you missed part 1, be sure to go back and listen to it. Don't forget to subscribe, leave us a comment, and share this episode with anyone who might benefit. We'll catch you next time. Until then, keep exploring, keep questioning, and keep learning.